Okay, so now let us go to the next topic within module 7, namely abstract Fourier analysis in Hilbert spaces. So far what we have been looking at are concrete examples of basis in Hilbert spaces. So we took the Hilbert space L2 of -1 1 and we produced the Legendre polynomials. We took L2 of the interval 0 infinity and we got the Laguerre functions, and we took L2 of the real line and we got the Hermite functions. These are classical examples of complete orthonormal systems in 3 important Hilbert spaces. Now let us take on a more abstract study of basis in Hilbert spaces. So suppose if H is a Hilbert space, let us take a basis B, which is a collection of vectors V alpha, where alpha ranges over a certain indexing set capital lambda. Now let us assume that this is a orthonormal basis, that is the vectors are all of unit length and they are mutually perpendicular. At this moment we are not going to assume that B is countable, we are going to assume that B is arbitrary. Remember that the Legendre polynomials form a countable orthonormal basis. The Hermite functions formed a countable orthonormal basis for L2 of the real line. Usually in all the examples that we shall encounter, the basis will be a countable orthonormal basis, but for the sake of theory let us not make this assumption. Spaces, Hilbert spaces in which uncountable orthonormal bases exist are huge entities, and you might wonder, do they really arise in interesting applications? Yes, they do, and in fact they arise in applications to differential equations and Fourier analysis, which is the theme of this lecture series, and so that is why I am not making the assumption that we are working with a countable basis necessarily. Where do they arise? They arise in the theory of almost periodic functions. I shall not get into this examples of bases of almost periodic functions. I have given you a reference on page 254 and 255 of this great book, classic book of Frederick Ries and Bélange. It is Ries-Nagy, the Hungarian mathematicians, and this book appeared in French and later in English, and the Dover reprint is available now and also available in Indian edition. It is one of the monumental treatises in functional analysis that has been around for nearly 90 years now. Okay, so now if you are given a basis V alpha and V is a vector in H, you take the inner product of V and V alpha and you get the scalar x alpha. The scalar x alpha is called the alphath Fourier coefficient of the vector V with respect to the given orthonormal basis B. Now we would like to consider the series summation x alpha V alpha, alpha belongs to lambda. Now before we embark upon this, think of the simple example, always begin with a simple example. Suppose you work with R3, R3 is a Hilbert space, right, with respect to the usual dot product, and you have an orthonormal basis E1 cap, E2 cap, E3 cap, and if you take a vector V, so what are the components of the vector with respect to E1 cap, E2 cap, E3 cap? It is V dot E1 cap is the first component x1, V dot E2 cap, that is the second component, and the third component is V dot E3 cap. This is a direct generalization of that idea. So x alpha can be thought of as the components of the vector V when you express this vector V in terms of this orthonormal basis, the collection of vectors V alpha. So now we have got a series x alpha V alpha, alpha belongs to lambda, but there is one small problem here. Remember that the family V alpha is not necessarily a countable family, it could be an uncountable family. So how do we make sense of a series of this type sigma x alpha V alpha where the number of terms is uncountable? We shall take up this issue now. First we shall prove a lemma. a very general lemma in real analysis. This has nothing to do with Hilbert spaces. So, suppose you have got an uncountable collection of non-negative real numbers. The numbers are non-negative and they are real numbers, and now we form this sum, summation A alpha, alpha belongs to lambda, display 7.7 in this slide. So, as it stands, this is an uncountable sum. So, how do we assign a meaning to this uncountable sum 7.7? What we do is very simple. We take finitely many indices alpha 1, alpha 2, alpha 3, alpha n, where the number of terms n is arbitrary and the indices alpha 1, alpha 2, alpha n are also arbitrary, chosen out of my indexing set lambda. And then you form the finite sum A alpha 1 plus A alpha 2 plus etc. plus A alpha n. So, take the set of all finite sums and then you take the supremum over the set of all finite sums. If this supremum is finite, then you assign this number as the value of 7.7. So, summation A alpha, alpha belongs to lambda, is a supremum of the set of all finite sums A alpha 1 plus A alpha 2 plus etc. plus A alpha n, where the supremum is over all the finite sums. Lemma says that if this sum 7.7 is finite, then all the terms must be 0 except possibly countably many. So, other than a countably many terms, all the other A alphas must be 0. So, if we have an uncountable collection of non-negative real numbers and if uncountably many of them are positive, then that supremum will be plus infinity. The supremum cannot be finite. So, the supremum that we are talking about is finite, then necessarily most of the A alphas must be 0 and the non-zero ones can only be countably many. So, in other words, effectively the sum 7.7 reduces to a countable summation. The uncountable sum 7.7 collapses to a countable sum. This is what the lemma is trying to tell you. The proof of the lemma is very easy. Suppose that uncountably many of the A alphas are non-zero, that means they are positive. So, let us look at the set En to be the set of all A alpha such that A alpha exceeds 1 upon n. So, look at these sets En, look at the union of these sets En. The union of these sets En is a set of all those indices alpha for which A alpha is positive. Because the moment A alpha is positive, then A alpha is going to exceed 1 upon n for some n with Archimedean property. Therefore, A alpha will become an element in En. So, it is very clear that the union of En is the whole set of all terms. Now, since we are assuming that uncountably many of them are positive, one of the sets En's must be uncountable. Let us call it E capital N. So, E capital N must be uncountable. Okay. So, now let us form the finite sums A alpha 1 plus A alpha 2 plus etc. plus A alpha n, where the A alpha 1, A alpha 2, A alpha n's are all coming from E capital N. But what is the definition of E capital N? The definition is that those elements in E capital N will all be bigger than 1 upon capital N. So, if you add up these things A alpha 1 plus A alpha 2 plus etc. plus A alpha n, it will exceed little n upon capital N. But now I can allow the little n to be as large as I want, and then I will get that these finite sums are unbounded. How can I take the little n to be as large as I want? Because E capital N is uncountable, so it in particular is infinite. So, I can take larger and larger number of terms out of En and I can add them up, but every term is bigger than 1 upon capital N. So, these finite sums A alpha 1 plus A alpha 2 plus A alpha n, these A alphas picked out of E capital N cannot be bounded, and then our supremum, namely our sum 7.7 is not finite, which is a contradiction. So, the lemma is complete. So, now let us return to Hilbert spaces. Now, let us immediately apply this to our problem of assigning a meaning to this infinite sum sigma x alpha v alpha, alpha belongs to lambda. What we will do is that we will prove that these scalar coefficients x alpha are 0 except for countably many indices alpha. In other words, this uncountable sum which is displayed collapses to a countable sum. Okay, so let us look at the Hilbert space setting now. We prove the following theorem. Suppose if V is an element of H, x alphas are the Fourier coefficients of V with respect to a given orthonormal basis B, which is a set of all V alpha such that alpha belongs to lambda. Then summation mod x alpha squared, alpha ranging over capital lambda, is finite, and all but countably many Fourier coefficients must vanish because this summation is finite. Sigma mod x alpha squared, alpha belongs to lambda, is finite. So, by appealing to the lemma, we will conclude that x alpha must be 0 for all but countably many indices alpha. So, x alphas are 0 for all but countably many indices alpha, which means that the sum sigma x alpha v alpha, alpha belongs to lambda, collapses to a countable sum. Further, this summation sigma x alpha v alpha actually converges and the sum is V. So, we have got lots of things to prove in this theorem. First thing to prove is that the first displayed sum is finite. We are going to repeatedly apply the Pythagoras' theorem, which you will have to recall. So, let us take a finite set of indices in lambda, okay, alpha 1, alpha 2, alpha n, and let us subtract off from V this finite linear combination x alpha 1 v alpha 1 plus x alpha 2 v alpha 2 plus etc. plus x alpha n v alpha n. So, let us take this difference. This vector is perpendicular to each of the vectors v alpha 1, v alpha 2, etc., v alpha n. So, let us check this. So, take this difference and take the dot product with v alpha 1. What are you going to get? V dot v alpha 1 minus x alpha 1 into v alpha 1 dot v alpha 1 minus x alpha 2 into v alpha 2 dot v alpha 1, etc. But remember that v alphas are orthonormal. So, v alpha 1 dot v alpha 1 is 1, v alpha 1 dot v alpha 2, v alpha 1 dot v alpha 3, they are all 0. So, we are simply left with v dot v alpha 1 minus x alpha 1 into v alpha 1 dot v alpha 1, which is 0 by definition of x alpha. So, we have checked that this difference v minus this finite linear combination is orthogonal to v alpha 1. Similarly, it is orthogonal to v alpha 2, etc., up to v alpha n. We have checked that claim. Now, once a vector is orthogonal to a bunch of vectors v alpha 1, v alpha 2, v alpha n, the vector will also be orthogonal to every linear combination of these vectors v alpha 1, v alpha 2, v alpha n. In other words, the difference v minus x alpha 1, v alpha 1 plus x alpha 2, v alpha 2 plus etc. is going to be orthogonal to x alpha 1 v alpha 1 plus x alpha 2 v alpha 2 plus etc. plus x alpha n v alpha n. So, we must now apply the Pythagoras' theorem. Pythagoras' theorem will immediately give you this displayed equation 7.8 in the slide, namely the norm squared v minus x alpha 1 v alpha 1 plus etc. plus x alpha n v alpha n plus norm squared x alpha 1 v alpha 1 plus etc. plus x alpha n v alpha n equal to norm squared v. So, now let us knock off one of the terms on the left hand side of 7.8. The first term I knocked off. What do I get? I simply get norm squared x alpha 1 v alpha 1 plus etc. plus x alpha n v alpha n squared less than or equal to norm squared v. Let us calculate the left hand side. X alpha 1 v alpha 1 plus x alpha 2 v alpha 2 plus etc. plus x alpha n v alpha n dot with the same thing, multiply it out. You will get the pure square terms, x alpha 1 squared v alpha 1 dot v alpha 1, but v alpha 1 dot v alpha 1 is 1. So, we will get mod x alpha 1 squared. Similarly, you will get mod x alpha 2 squared, etc. You will get mod x alpha n squared. Then you will get the cross terms, x alpha I, x alpha j, v alpha I dot v alpha j. But remember that our vectors v alpha are orthogonal. So, if I is not equal to j, v alpha I dot v alpha j is 0, the cross terms all disappear and we simply get the last display in the slide, and the left hand side of the inequality simply becomes mod x alpha 1 squared plus mod x alpha 2 squared plus etc. plus mod x alpha n squared, which basically means the sum of the squares is less than or equal to norm v the whole squared. Okay. So, these finite sums mod x alpha 1 squared plus mod x alpha 2 squared plus etc. plus mod x alpha n squared are all bounded above by a fixed number norm v squared, which basically means that uncountable sum summation mod x alpha squared, alpha belongs to lambda, is finite, and hence all but countably many of the x alphas must be 0. That is, all but countably many of the Fourier coefficients must vanish. The uncountable sum collapses to a countable sum. Okay, that proves the first part of the theorem. Now, we got to go to the second part of the theorem. So, since the sum collapses to a countable sum, we ignore all the 0 terms and we get simply 7.9. X alpha 1 v alpha 1 plus x alpha 2 v alpha 2 plus x alpha 3 v alpha 3 plus dot dot dot. So, now we must study this infinite series, the genuine honest infinite series 7.9 that you see in the display, and all the coefficients x alpha j are not 0 in the display 7.1 because we have omitted all the 0 terms. Now, we shall prove that this series 7.1 converges in H, that is, it converges in norm, and for that we first observe that mod x alpha 1 squared plus mod x alpha 2 squared plus mod x alpha 3 squared plus etc. converges as we have just seen, and hence its partial sums form a Cauchy sequence, namely limit as n tends to infinity mod x alpha n squared plus mod x alpha n plus 1 squared plus etc. plus mod x alpha n plus k squared equal to 0 for all k. So, now let us prove that the partial sums of 7.9, we shall show that the partial sums of 7.9 form the Cauchy sequence, and a Hilbert space is a complete metric space, and if your sequence is Cauchy, then it must converge. So, the partial sums of 7.9 will then converge. Finally, we have to show that the sum is exactly V. All right. So, let us show its Cauchy. So, let us take the norm squared of x alpha n v alpha n plus x alpha n plus 1 v alpha n plus 1 plus etc. plus x alpha n plus k v alpha n plus k. This norm squared will exactly be mod x alpha n squared plus mod x alpha n plus 1 squared plus etc. plus mod x alpha n plus k squared. And the RHS tends to 0 as we have just seen, the very top display in the slide, and therefore, the partial sums form a Cauchy sequence, and that job is done. So, now we have to show finally that the series 7.9 converges to V. So, let epsilon greater than 0 be arbitrary. What do we know? What is our fundamental assumption? We have a basis. We have a basis. So, what is our basis? Our basis is this set B, which is a set of all B alphas. What do you mean by saying that B is a basis? It means if I take the set of all finite linear combinations of elements of B, it is dense in H. That is the meaning of basis in a Hilbert space. Now, we need to use this fact that B is a basis. So, it means that given any epsilon greater than 0, there are finitely many scalars y alpha 1, y alpha 2, y alpha n such that the linear combination y alpha 1 v alpha 1 plus y alpha 2 v alpha 2 plus etc. plus y alpha n v alpha n approximates v to within less than epsilon in norm. That means norm squared v minus y alpha 1 v alpha 1 plus y alpha 2 v alpha 2 plus etc. plus y alpha n v alpha n is less than epsilon squared by 2. The epsilon squared by 2, the factor of 2 in the denominator, is a convenience, as you understand now. Now, we can take this capital N as large as you want, because I can always add 0 coefficients. Nobody says the y alpha j's should be non-zero. So, by throwing in 0 coefficients, I can assume that the n is as large as we wish. How large should I take the n? It's very simple. We take the n to be so large that mod x alpha n plus 1 squared plus mod x alpha n plus 2 squared plus etc. plus mod x alpha n plus 3 squared etc. is less than epsilon squared by 2. Remember that the sum of the squares of the x alpha converges and so forms a Cauchy sequence. So, this tail of the convergent series is less than epsilon squared by 2. So, now let us observe again, as in the previous argument, that v minus x alpha 1 v alpha 1 plus x alpha 2 v alpha 2 plus etc. plus x alpha n v alpha n is orthogonal to each of the vectors v alpha 1 v alpha 2 v alpha n, and hence it is orthogonal to every linear combination. And so, v minus x alpha 1 v alpha 1 plus etc. plus x alpha n v alpha n is orthogonal to x alpha 1 minus y alpha 1 v alpha 1 plus etc. plus x alpha n minus y alpha n v alpha n. Now, we must apply the Pythagoras' theorem. No prizes for guessing. Apply the Pythagoras' theorem, and what do we get? We get norm squared v minus y alpha 1 v alpha 1 plus etc. y alpha n v alpha n squared equals norm of v minus x alpha 1 v alpha 1 plus etc. plus x alpha n v alpha n squared plus norm squared of the remaining term, mod x alpha 1 minus y alpha 1 squared plus etc. plus mod x alpha n minus y alpha n squared. So, you knock off one term as usual, we will conclude that norm of v minus x alpha 1 v alpha 1 plus etc. plus x alpha n v alpha n squared less than epsilon squared by 2. Now, we have come so far. Now, let us assume that little n is bigger than capital N. Then Pythagoras' theorem again will tell you that norm of v minus x alpha 1 v alpha 1 plus da 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 plus x alpha n v alpha n squared equals norm of v minus the linear combination up to capital N, namely norm squared v minus x alpha 1 v alpha 1 plus etc. plus x alpha n v alpha n plus the norm square of the remaining term. The norm square of the remaining term is what? Mod x alpha n plus 1 squared plus etc. plus mod x alpha n squared. So, now that is less than epsilon squared by 2 plus epsilon squared by 2, which is epsilon squared. So, we have proved that if little n exceeds capital N, then norm of v minus x alpha 1 v alpha 1 plus x alpha 2 v alpha 2 plus etc. plus x alpha n v alpha n is less than epsilon, which means the series 7.9 converges to V in the Hilbert space norm. So, the proof of the theorem is completed.